11.2 is page 777, Vectors in Space. When we get to section 11.2, we finally understand why we paired those couple of sections in chapter 6 with these couple of sections in chapter 11. Because if you look at our note sheet, it's literally all the exact same formulas that we had in chapter 6, right? In chapter 6, we worked in 2 dimensions. In chapter 11, we're working in 3 dimensions. But other than that, everything is going to be the same. So you'll notice that when you have a vector in component form, it's still going to have v1, v2, but it's going to have that 3rd dimension, v3. So just like we saw yesterday with section 11.1, like let's say with the distance formula, because you knew how to find the distance formula using the distance formula when you had 2 dimensions, you just repeated that same process, that same pattern one more time for the 3rd dimension. That's exactly what I want to do here. We've learned that for component form of a vector, you take your stopping point minus your starting point. So when we did this in 2 dimensions, we did q1 minus p1, and then we did q2 minus p2. So follow that same pattern one more time for the 3rd dimension, and just say q3 minus p3, and that'll be the 3rd piece of our component form. Magnitude. For magnitude, we took the component form of the vector, v1 and squared it, and v2 and squared it, added those values together and took the square root. Before we take the square root, just include that 3rd part of the component form. We had unit vector form. It was v1i plus v2j, so here's the 3rd part of that. It's going to be v3k. The formula that we had for a unit vector in the direction of v is exactly the same. To add 2 vectors, we start with the exact same way we did it in 2 dimensions and continue that pattern for 3. Same thing if we have scalar multiplication. If we multiply a vector times a constant, we're just going to multiply all 3 parts now. For dot product, we'll find the product of the first pieces, the product of the second pieces, and the product of the third pieces, and then add those together. Angle between the 2 vectors, that formula is exactly the same, as is the definition of orthogonal and parallel. 2 vectors will still be orthogonal if their dot product is 0, and they'll still be parallel if one is a multiple of the other. Okay? So example number 1. For example number 1, it says find the component form and the length of the vector that has an initial point of 3, 4, 2 and a terminal point of 3, 6, 4, and then find a unit vector in the direction of v. So again, remember, they have to tell you the stopping point and the starting point. It matters. Order makes a difference. So we're going to go through and we're going to say stopping point minus starting point, 3 minus 3. Stopping point minus starting point, 6 minus 4. And then do that one more time, stopping point minus starting point, 4 minus 2. So what will you get for the component form of this 3-dimensional vector? Yes, 0, 2, 2. All right, then let's find its magnitude. To find its magnitude, we can put 0, 2, and 2 into our formula. So square root of 0 squared is 0, plus 2 squared is 4, plus 2 squared is 4. So we'll get square root of 8. And we always want to give our radicals in lowest form. So since 8 is just 4 times 2, we could say the square root of 4 is 2, so 2 squared roots of 2. Unit vector in the direction of v, our formula was to take the vector and divide it by its magnitude. So our vector was 0, 2, 2. Let's divide it by that magnitude that we just found. The magnitude that we just found was 2 square roots of 2. So we'll do 0 divided by 2 square roots of 2 is 0. 2 divided by 2 square roots of 2, the 2's are going to drop each other out and just leave me 1 over the square root of 2, and we'll rationalize that in just a sec. And then same story here, these 2's will drop out and we'll have 1 over the square root of 2. So to get rid of that radical in the denominator, if we rationalize, multiply top and bottom by the square root of 2, and we'll have 0 square root of 2 over 2, square root of 2 over 2. All right, so this time they give me two different vectors. In example number 3, they give me 1, 0, 2 and 3, 1, 0, and they ask me to find the angle between those two vectors. Now, something else that they typically ask me to do is determine whether the vectors are parallel, orthogonal, or neither. So let's catch this at the same time here. And something else that they often ask us to do is find the dot product of two vectors. So let's do all of that here together to minimize our work. All right, so let's start with dot product, since we need that for both the angle between the two vectors and we need that to determine if we're parallel, orthogonal, or neither. So if we do dot product, we're going to multiply the first values, multiply the second values, and multiply the third values. So what do you get for your dot product? 3. So what do I know about parallel, orthogonal, neither if my dot product is 3? It's not orthogonal, right? How do I know that? Dot product is not 0, right? So if they're not orthogonal, let me check and see if they're parallel. How do we know if they're parallel?
One is a multiple of another.
Yes, one is a multiple of another. So I'm going to go through, I'm just going to pull the first value to analyze instead of having to write those three-dimensional vectors. I'm going to say if u is a multiple of v, that means that u is equal to k times v, then 1 would have to be equal to some number times 3. So 1 would have to be equal to some constant times 3. So you can use logic to figure that out and say, okay, well, 1/3 times 3 is 1. Or you can solve that formula algebraically, divide both sides by 3, and you'll get k is equal to 1/3. So that worked for the first value. I don't know if it'll work for every value. I'll have to check that and see. So let's try it. Let's go back and see. If I take vector u, is it equal to 1/3 times vector v? Well, 1/3 of 3 was what gave us 1. We know that would work because that gave us our formula. But 1/3 of 1 doesn't give me 0. And 1/3 of 0 doesn't give me 2. So if we didn't have a dot product of 0, they weren't orthogonal. Since one is not a multiple of the other, then they're not parallel. So then I'm going to say that they're neither. All right, well then let's find the angle between the two vectors. We know they're not at a 90-degree angle since they're not orthogonal. Let's see what they are. So in my numerator, I need the dot product. We already found that a second ago. It was 3. So let's work on the magnitudes in the denominator. So first off, magnitude of u. That's going to be square root of 1 squared plus 0 squared plus 2 squared. So square root of 1 squared plus 0 squared plus 2 squared. So that's going to give us square root of 5. All right, figure out what your magnitude for v would be. Calculate your magnitude for v. All right, what'd you get? Square root of 10, yes. Now, you can go ahead and throw this whole thing in your calculator right now, inverse cosine of that value. I usually like to simplify them because sometimes they simplify down to one of those values we had memorized, and then it makes it seem a little more logical to us where that angle came from. But you don't have to do that. So in my denominator, I would have the square root of 50. So that's just 25 times 2, so that'd be 5 square roots of 2. And I wouldn't leave that radical square root of 2 in the denominator, so when I multiply top and bottom by that radical, then I get 3 square roots of 2 out of 10. So, yeah, that's not one of those values that we had memorized earlier. So, again, you could do inverse cosine of this, inverse cosine of this, or inverse cosine of this. Doesn't make any difference. You're going to get the exact same answer. For a quiz tomorrow, we want to be sure we have our scientific calculator, because when you get right here, you don't have a way of finding this value if you don't have a scientific calculator, right? So be sure you have that with you. So inverse cosine of that answer will give us our angle between the two vectors, 64.9. All right, the last thing that we want to look at today, again, we're not doing the remainder of section 11.2 where they're talking about equilibrium and collinearity and that type of thing. But one thing that we do want to pick up from section 11.3 is the idea of cross product. We mentioned before that there are actually two ways to multiply vectors, and so we needed different names for them. And so we call one dot product and we call one cross product, just because when we write multiplication, sometimes we put a dot in between the numbers and sometimes we put a little x in between the numbers to show multiplication. So that's why we call them dot product and cross product, just to differentiate. The formula for cross product is pretty obnoxious. They show me right here, this is how I find the cross product of two vectors. And I don't know, that just looks like a bunch of craziness to me. It's a little easier for me to do if I understand where that comes from. Cross product actually comes from evaluating the determinant of a 3 by 3 using minors and cofactors using row number 1. First off, I have to build that 3 by 3. The first row in my 3 by 3 is going to be the standard unit vectors I, j, k. The second row is going to be whatever the first vector is in my cross product. So this was u, so we've got u1, u2, u3. The second vector goes in the third row, so we had v1, v2, v3. So standard unit vectors I, j, k, the first vector from your cross product, the second vector from your cross product. And then we're going to evaluate that with minors and cofactors using row number 1. So that would be I times its minor, j times its minor, k times its minor. I times its minor, j times its minor, k times its minor. To find the minor, remember you have to eliminate the row and the column that is in. So like if I'm looking at A, if I'm looking at I, I'm going to eliminate this row and this column. And what I would be left with is U2, U3, V2, V3. That's where this comes from. Additionally, the checkerboard matrix tells me to go plus, minus, plus. So plus, minus, plus. Once I have that, then to evaluate a 2 by 2 determinant, I just do U2, V3 minus U3, V2. U2, V3 minus U3, V2. So you can utilize that formula if you want to find the cross product, or you can just build a 3 by 3 determinant and evaluate it. So let's say in example number 1, they give me two vectors. They could give it to you in standard unit vector form or in component form. If you don't like the standard unit vector form, you can switch it to component form as we've been doing. So to find the cross product of u and v, my first row is going to be I, j, k, the standard unit vectors. My second row is going to be whatever comes first. Vector u came first, so I'm going to put in 1, 2, 1. The third row will be the vector that came second, so my vector that came second was 3, 1, 2. So there's my 3 by 3 that I'm going to find the determinant of. Going to use the first row with minors and cofactors, and again remember it goes plus, minus, plus according to the checkerboard matrix. So for the minor of I, I'm going to eliminate the row and the column, and what's left is 2, 1, 1, 2. For the minor of j, I'll eliminate the row and the column, and what's left is 1, 1, 3, 2. For the minor of k, I'll eliminate the row and the column, and what's left is 1, 2, 3, 1. And then I can just do my little 2 by 2 determinants. So I could say, okay, 4 minus 1, 2 minus 3, 1 minus 6. 4 minus 1 gives me 3. 2 minus 3 is a negative 1, so negative 1 times negative j is going to be a positive 1j. And then here, negative 5k. And again, that's the standard unit vector form, or you're also welcome to write it in component form. Now, on the bottom of page 785, they give me some algebraic properties of cross product that are really helpful. Look at the first one. The first one says u cross v is just the opposite of v cross u. So if they ask me to find u cross v and then right behind it they say v cross u, I don't have to go through all of this work that we just did up here. All I have to do is say, well, that's going to be the opposite of what I just got. A second ago, I got 3, 1, negative 5. So the opposite of that is just going to be -3, -1, +5. If I actually went through and did that whole cross product process, I'd get that same answer. They also tell me a little further down on that table on page 785 that if you cross a vector with itself, you will always get the 0 vector. So u cross u, without even knowing what u is automatically 0. They also tell me that if I cross any vector with the 0 vector, it is also going to be 0, no matter what that vector is. Okay? All right, so here is our homework for tonight on 11.2 and 11.3.